The various bargaining models we've studied so far all involve two negotiators bargaining over a unit of surplus. We'll now study a model of multilateral bargaining when there's more than two players. To keep things simple for this particular discussion, we'll stick to 3 players. So the outcome of the bargaining process is a division of the surplus, which is a vector x1, x2, and x3, such that x1 plus x2 plus x3 equals 1. So this total unit of surplus is divided among the 3 players, 1, 2, and 3. Player 1 gets x1, player 2 gets x2, and player 3 gets x3. And the sum of those obviously has to be equal to the total amount to divide, which is 1. We'll study a very simple bargaining model here. There are infinitely many periods. In the first period, player 1 makes a proposal. The others, so players 2 and 3, vote to either accept or reject. If they both accept it, whatever division of the surplus player 1 proposed is the division of the surplus, and the game ends. If even one of them rejects, then the game proceeds to the next period. So the voting rule here is that there needs to be unanimity. Everybody has to agree that this proposal is acceptable. Otherwise, the game proceeds to the next period. In the second period, player 2 proposes. Again, the others vote, the others being 1 and 3, and the rest of the game proceeds exactly as before. If 1 and 3 both accept, the game ends with player 2's proposal being the division of the surplus. If even one of 1 and 3 rejects, then the game proceeds to the third period. In the third period, player 3 proposes, and then the others vote, and the others, of course, being 1 and 2, and everything else is just as in the earlier periods. This goes on. In period 4, we go back to player 1, and we just cycle through the proposers until some proposal is finally accepted. We're going to assume that there's a common discount factor, so everybody has the same discount factor delta. This will just keep our life a little bit easy to make this exercise simple to analyze. So what we want to do is find a subgame perfect equilibrium. We're going to look for a stationary subgame perfect equilibrium. The reason we can look for a stationary subgame perfect equilibrium is because this game is stationary. Let me scroll back here and we'll see that this game is indeed stationary. If we look at the game that starts at the initial node of the game and we compare that with the game starting in period 4, it's identical. So the game is indeed stationary. There's also a symmetry to this game. The game in period 1, from player 1's perspective, is exactly the same as the game in period 2 from player 2's perspective, and the game from player 3's perspective in period 3, and so forth. We can leverage this in looking for a symmetric, stationary subgame perfect equilibrium. We'll look for an equilibrium where, in each round, the proposer proposes a division of the surplus according to XP is what the proposer keeps for herself, XN is what the proposer offers to the player who will be the next proposer, so the player who will propose in the next round, and XL is the amount that the proposer offers to the player who was the proposer in the previous round, or will be the proposer in 2 rounds rather than the next round. So XP is what the proposer keeps, XN is what the proposer offers to the player who will propose in the next round. For example, XN is what player 1 will offer to player 2 in the first round, because player 2 will be the next proposer. And XL is what the proposer offers the player who proposed in the previous round. So in the last period, whoever proposed, they are offered XL. So in period 2, for example, player 2 will offer player 1 XL. In period 1, player 1 is going to offer XL to player 3, because remember, except for the first period, in every other period, the player who proposes 2 periods from now is the one who proposed in the last period. So you can think of this as being the amount that you offer to the player who proposed on the last period, or what you offer to the player who will propose not next round, but the one after that. It's the same thing. In equilibrium, the proposal should be accepted, so the next round's proposer would get, if they reject, they'll get delta XP, because they'll be the proposer next time. So if they vote to reject, they'll get delta XP. So in order to accept, they have to be offered at least delta XP. So in order for next period's proposer to vote to accept, it has to be that what is being offered to them is at least as good as their continuation value, which is delta XP. Because if they reject, that's what they're going to get. Similarly, if the proposer 2 periods from now, or the proposer from last period, if she rejects the proposal from today, then she will be the next proposer tomorrow, and so she can get XN tomorrow. That's as good as getting delta XN now. So for her to vote to accept, it has to be that XL is at least delta XN. Remember that the proposer wants to keep as much for herself as she can. So she's going to set xn equal to exactly delta xp and xl equal to delta xn, which is in turn equal to delta xn times delta xp, so it's delta squared xp. Now we know that xn plus xp plus xl has to equal 1. So xp plus delta squared xp equals 1. Therefore, xp equals 1 over 1 plus delta squared. And then once we know that, then we can multiply that by delta to get xn. Xn is delta divided by 1 plus delta squared. And xl is delta squared divided by 1 plus delta squared. We solved for a stationary subgame perfect equilibrium of this bargaining game. In each period, the proposer will keep this much for herself, will offer the next period's proposer this much, and the proposer from 2 rounds in the future, or the proposer from the last round, will get this much. And the next round's proposer and the proposer from 2 rounds from now will both vote to accept if they get at least this much. That's a stationary subgame perfect equilibrium. It's important to note here that there are other equilibria than this stationary equilibrium. Moreover, we've looked at a very simple bargaining game where the voting rule is unanimity. So everybody has to agree to accept a proposal. It's easy enough to see that the game's a little more complicated, but not too much more if you have something like a majority voting. So maybe as an exercise, you want to look at the case where you have majority voting, where only 2 out of the 3 players would have to agree in order to implement a proposal. So in this case, you'd have one proposer, and as long as one of the 2 other players accepts, the game would end. So you might, as an exercise, think about how that changes the payoffs. You'll probably find that player 3 is not going to do so well.